Swayam Prabha. Digital India. Educated India.
We will continue the lecture on solving linear equations. In the last lecture, I discussed the case of many more equations and variables where we might not have a solution and how we can use an optimization perspective to find a solution. In this lecture, I am going to give you some examples for that case, show you what happens when we apply the solution that we derived last time. And then after that I will go on to look at the case of more variables than equations. So let us look at an Ax equal to b example system as shown in the screen. Here we have a matrix with 3 rows and 2 columns, which basically means that there are 3 equations in 2 variables, number of equations more than number of variables. And we have to read these equations as x1 equal to 1, 2x1 equal to minus 0.5 and 3x1 plus x2 equal to 5. So if you notice these equations, you would realize that the first 2 equations are inconsistent. For example, if we were to take the first equation as true, then x1 equal to 1, and if we substitute that value into the second equation, you will get 2 equal to minus 0.05. If you were to take the second equation as true, then 2x1 is minus 0.5, so x1 will be minus 0.25, and that would not solve the first equation. So these 2 equations are inconsistent. The third equation, since it is 3x1 plus x2, irrespective of whatever value you get for x1, you can always use this equation to calculate a value for x2. However, we cannot solve this set of equations. Now let us see what is the solution that we get by using the optimization concept that we described in the last lecture. We said x equal to A transpose A inverse A transpose B. The A matrix is 1 0 2 0 3 1. So the A transpose matrix is 1 2 3 0 0 1. Simply plugging in the matrices here and then doing the calculation gives us this equation, which says x1 x2 is a matrix times 15 5. This is an intermediate step for the calculation, and when you further simplify it, you get a solution x1 equals 0, x2 equal to 5. Notice that the optimum solution here that is chosen does not have either one of the 2 cases that we talked about in the last slide, which is x1 equal to 1 and x1 equal to minus 0.25. The optimization approach chooses x1 equal to 0 and x2 equal to 5, and when you substitute it back into the equation, you get b as 0 0 5, whereas the actual b that we are interested in is 1 minus 0.5 5. So you can see that while the third equation is being solved exactly, the first both the first 2 equations are not solved for. However, as we described before, this is the best solution in a collective minimization of error sense, which is what we defined as minimizing sum of squared of errors. We will now move on to the next example. Let us consider another example for us to illustrate something different here. We have taken the same left hand side, we have the same A matrix. However, the right hand side has been modified to be 1 2 5. We have done this for a specific reason, which we will see presently. So when you look at this equation, if you take the first equation, it reads as x1 equal to 1. If you look at the second equation, it reads as 2x1 equal to 2. The third equation reads as 3x1 plus x2 equals 5. So from the first equation, you can get a solution for x1 equal to 1, and the second equation, since it reads as 2x1 equal to 2, we have to simply substitute the solution that we get from the first equation and see whether the second equation is also satisfied. Since x1 equal to 1, 2 times x1, 2 times 1 is 2, the second equation is also satisfied. Now let us see what happens to the third equation. The third equation reads as 3x1 plus x2 equals 5. We already know x1 equal to 1 satisfies the first two equations. So 3x1 plus x2 equal to 5 would give you x2 equal to 2. Now you notice that if I get a solution 1 and 2 for x1 and x2, though the number of equations are more than the variables, the equations are in such a way that I can get a solution for x1 and x2 that satisfies all the three equations. Now let us see whether the expression that we had for this case actually uncovers this solution. So we said x equal to A transpose A inverse A transpose B, and we do the same manipulation as the last example, except that this B has become 1, 2, 5 now. After some more calculations, you will see that x1 equal to 1, x2 equal to 2, thus the solution is 1, 2, and we had already verified that this would solve the equation, and we had verified that 1, 2 is a solution that we can directly get by observation from the previous slide. So the important point here is that if we have more equations than variables, then you can always use this solution, least square solution, which is A transpose A inverse A transpose B. The only thing to keep in mind is that A transpose A inverse exists if the columns of A are linearly independent. If the columns of A are not linearly independent, then we have to do something else, which you will see as we go through this lecture. So that finishes the case where the number of equations are more than the number of variables. Now let us address the last case where the number of equations are less than the number of variables, which would be m less than n. In this case, we address the problem of more attributes or variables than equations. Now since I have many more variables than equations, I would have infinite number of solutions. The way to think about this is the following. If I had, let us say, 2 equations and 3 variables, you can think of this situation as one where you could choose any value for x3 and then simply put it into the 2 equations, and whatever are the terms with respect to x3, you collect them and take them to the right hand side. That would leave you with 2 equations and 2 variables, and once we solve for that 2 equations and 2 variables, we will get values for x1 and x2. So basically what this means is that I can choose any value for x3, and then corresponding to that I will get values for x1 and x2, so I will get infinite number of solutions. Since I have infinite number of solutions, then the question that I ask is, how do I find one single solution from the set of infinite possible solutions? Clearly, if you are looking at only solvability of the equation, there is no way to distinguish between these infinite possible solutions. So we need to bring some other metric that we could possibly use, which would have some value for us to pick one solution that we can say is a solution to this case. Similar to the previous example, we are going to take an optimization view. Here what we are going to do is we are going to minimize x transpose x. This half is just to make sure the solution comes out in a nice form. And notice here something that is important. We also have a constraint for this optimization problem. S dot t dot means subject to. So I want to minimize this half x transpose x subject to the constraint Ax equal to b. So in other words, what we are saying is, whatever solution we get for x, that has to necessarily satisfy this equation, and this is not a problem. We can find infinite number of solutions x which will satisfy these equations. So what this objective does is, of all of those solutions, how do I pick that one solution which will minimize this x transpose x? We have to think about a rationale for why we would choose x transpose x as an objective. This basically says that of all the solutions, I want the solution which is closest to the origin, is what this is saying in terms of x transpose x. From an engineering viewpoint, one could justify this as the following. If you have lots of design parameters that you are trying to optimize and so on. You would like to keep the sizes small, for example, so you might want small numbers, so you want to be as close to origin as possible. This is just one justification for doing something like this. Nonetheless, this is one way of picking one solution from these infinite number of solutions. Now, in the previous example and in this example, we are solving these optimization problems. However, we have not taught in this course how to solve optimization problems. For people who already know how to solve optimization problems, this would be obvious. For other participants who don't know how to solve optimization problems, I would encourage you to just bear with me and then go through this solution and see what the solution form is. And once this module on linear algebra is finished, we will have a couple of modules on optimization from the viewpoint of data science. So when we do that, you will see how we solve these kinds of optimization problems. The optimization problem that we solved for the last case is what is called an unconstrained optimization problem, because there are no constraints to that problem, whereas this problem that we are solving is called a constrained optimization problem, because while we have an objective, we also have a set of constraints that we need to solve. So you'll have to bear with us till you go through the optimization module to understand this. Interestingly, it is generally a good idea to teach linear algebra and optimization, but interestingly, some of the linear algebra concepts you can view as optimization problems, and solving optimization problems requires lots of linear algebra concepts. So in that sense, they are both coupled. In any case, to solve optimization problems of this form, we can define what is called a Lagrangian function, f of x comma lambda. Lambda are extra parameters that we introduce into this optimization formulation, and what you do is you minimize this Lagrangian with respect to x to get a set of equations, and you also minimize this with respect to Lagrangian, which will back out the constraint. So whatever solution you have has to solve both the differentiation with respect to x, which should give you x plus A transpose lambda equal to 0, and also differentiation with lambda, which will simply give you Ax minus b equal to 0. That would basically say that whatever solution you get, that has to satisfy the equation Ax equal to b. We will see how this is useful in identifying solution. So let's look at this equation, x plus A transpose lambda is 0. So from this we can get a solution for x, which is minus A transpose lambda. Now what you could do is, you don't know x and you don't know lambda also, so there has to be some way of finding out both of them. So what we are going to do is, we are going to use the knowledge that any solution that we get has to satisfy the equation Ax equal to b. So what we are going to do is, we are going to pre-multiply this x by a. So we pre-multiply on both sides, so we get Ax equal to minus A transpose lambda by pre-multiplying this equation by a. Now since any solution x satisfies Ax equal to b, I can replace this Ax by b, and I get this equation b equal to minus A transpose lambda, and from this equation we can get lambda to be minus A transpose inverse b, and this is possible and this inverse exists only if all the rows are linearly independent. Now since we have an expression for lambda, we can substitute that expression here, and we will get x equal to minus A transpose lambda, and here lambda is this expression which is from here. So this satisfies, this solves for x in the equation Ax equal to b, and since we use this idea here, the x that we get is such that Ax equal to b, that is satisfies the original equation. Now let's take an example to understand this. I have an Ax equal to b here. I have A as 1 2 3 0 0 1 and b as 2 1. So again notice here, since there are two equations, I have two rows, and 3 equations, 3 variables, I have 3 columns, and these equations are read as x1 plus 2x2 plus 3x3 is 2 and x3 equals 1. Now clearly when you look at this equation, you will notice that x3 equal to 1 has to be a solution. So the question is, how do I choose x1 and x2? Nonetheless, we will use the optimization solution to actually see what happens here. So the optimization solution from the previous slide is the following: x equal to A transpose inverse B. Now A transpose is 1 2 3 0 0 1 here, and this is my A, and A transpose again I take an inverse of this, and B now is 2 1. And when I do some more algebra, I finally get a solution to x1 x2 x3, which is the following, and we had already seen that x3 equal to 1 has to be a solution because the last equation basically said x3 equal to 1. Now x1 and x2, you could have found several numbers to satisfy the first equation after you choose x3 equal to 1. Of all of these, this solution says this minus 0.2 minus 0.4 is the minimum norm solution, or this vector is the closest vector from the origin that satisfies my equation Ax equal to B. So I can finally say my solution x1 x2 x3 is minus 0.2 minus 0.4 1, and you can easily verify that this satisfies the original equation. Since x3 is 1, the second equation is x3 equal to 1, so that gets satisfied. When you look at the other equation, you have 1 times minus 0.2 plus 2 times minus 0.4, that will be minus 0.2 minus 0.8 1 plus 3 times 1 will give you 3 minus 1 equal to 2, which is this. So the solution that we found satisfies the original equation, and this also turns out to be the minimum norm solution as we discussed. So when we have a set of linear equations, we basically said that there are 3 cases that one needs to look at. One case is where number of equations and variables are the same, m equal to n. The second case is where the number of equations are a lot more than the number of variables, m greater than n. And the third case was when number of equations less than number of variables, m less than n. And we saw that one case is an exact solution if it's a full rank matrix, and if it's not a full rank matrix, then you could have infinite solutions or no solutions. And interestingly, the next 2 cases covers these 2 aspects. When I have lot more equations than variables, I have a no solution case, and when I have lot more variables than equations, I have infinite solution case. And since we are able to solve all the 3, we should be able to use the solution to the case 2 and 3 for the case 1 where the rank is not full, and depending on whether it is a consistent set of equation or inconsistent set of equation, you should be able to use the corresponding infinite number of solutions or no solutions result, right. So in some sense we understand that there should be some generalization of all of these results, so that we can write one equation which solves all of these cases, square, rectangular cases and so on. So that's the question that we are asking. Is there any form in which the results obtained from cases 1, 2 and 3 can be generalized? It turns out that there is a concept that we can use to generalize all of these. This is what is called the Moore-Penrose pseudo-inverse of a matrix. So when we typically have equations of the form Ax equal to B, we write x equals A inverse B as the solution. The generalization of this is to write x is A plus, I have used this term to denote the pseudo inverse B, and as long as we can calculate the pseudo inverse in a fashion that irrespective of the size of A, irrespective of whether the columns and rows are dependent or independent, if I can write one general solution like this, which will reduce to the cases that we discussed in this lecture, then that is a very convenient way of representing all kinds of solutions. Instead of looking at whether the number of rows are more, number of columns are more, is the rank full, and so on, all of that, if they can be subsumed in one expression like this, it would be very nice. And it turns out that there is an expression like that, and that expression is called the pseudo inverse. Now the pseudo inverse A for A can be calculated using singular value decomposition as one technique. There are many other ways of computing this, but singular value decomposition is one way of computing this. And as far as this course is concerned, you just need to know that we can compute this. We do not have to really worry about how singular value decomposition is done. So let me summarize this lecture. We said we are interested in solving equations of the form Ax equal to b. We talked about three cases, m equal to n, and m, if A is full rank, unique solution A inverse b. If A is not full rank, there are two possibilities, either the equations are consistent or inconsistent. And if m is greater than n, we look at a least square solution, and if m is less than n, then we look at a least norm solution. We can write this as A inverse b, or I could also write this as pseudo inverse b. In this case, the pseudo inverse and A inverse will be exactly the same. And as I mentioned before, since these two cases are covered by these two, I should be able to use the same A pseudo inverse b for both these cases also, without worrying about whether they are consistent, inconsistent, and so on. In all of these cases, I will get a solution by using the idea of generalized inverse. So this concludes the section on solving linear equations, irrespective of whether it's a square or a rectangular system, or not worry about really whether the columns are dependent, independent, and so on. You can use generalized inverse as one unifying concept to find a solution to all these cases. Thank you, and in the next lecture we will take a geometric view of the same equations and variables that is useful in data science.